Hello students, so today what we were going to do is actually we will be talking about the work done by gas. Now in our last class we have seen that the laws of thermodynamics, the first law of thermodynamics states that whenever we provide some heat energy to some gas system, it is utilized in two ways. One is to increase the internal energy of that gas, and some amount of work done uh, is being done because of that extra energy which is given to the gas system. Now this extra energy we have told about P delta V though, but this is not the case which happens all the time. So we will be talking about different processes in this class. So what are the thermodynamic parameters? Let us remind at first. So the thermodynamic parameters are pressure, temperature and volume. Now variation of these thermodynamic parameters uh, will create different situations, and as a result we get different processes. Now what are the processes we have, and uh, how the work done is being done on that system, we will be looking into it. So the first one is called isobaric process. Isobaric process. So the isobaric process means, you remember about barometer. So baro, the word bar baro is regarding with the pressure. So isobaric means the pressure here is kept constant. Now as the pressure is constant, we have seen that delta W is our delta P into delta V, right? So here we can always write in differential from dW is P dV. Okay, now what is that? Like if I have a system of gas in some sort of piston mechanism, then if there is a slight change in volume of del dV, then the work done is dW. So as a result, if I change the volume from V1 to V2, then what will be the work done? The work done will be integration of dW, that is W, that will be in that side, integration of P dV from V1 to V2. Now in this case we can see that pressure is constant, so it can come out of our integration and we get V1 to V2 dV. So we can write P V2 minus V1. So this is the work done in our isobaric process where pressure is kept constant. Now let us talk about the next process, which is called our isochoric process. Isochoric process. Now what is our isochoric process? Isochoric process means the volume is being kept constant. So whenever the volume is kept constant, uh, obviously the change in delta V will be zero instantly. So if I write W, that is integration of dW, that will be integration of P delta V, that is dV. Now we know that the change of volume is zero, so the whole term will be zero. So in case of isochoric process where volume is kept constant, the work done is always zero. Let us talk about another process. So we have made pressure equal to constant. We have also checked volume is constant. That means the piston will be fixed. So this will be fixed. Okay, and the process will be as usual, and the temperature will be given. So only the energy that is being provided, that energy will be used to increase the internal energy of that gaseous system, Moving to the next one, where the third thermodynamic parameter we will be kept constant. So that will be kept constant, that is temperature. So when we keep our temperature constant, then the process is called isothermal process. So in isothermal process, the temperature is kept constant. So how we will be deriving that? So we know that our W is integration of P dV. Now we know that we have to somehow involve this temperature variable with our pressure and volume. Now we know that for isothermal process, some conditions we have to follow. The process has to be a quasi-static process. Quasi-static. So we will be talking about this now. What is a quasi-static process? Quasi-static process has to be, then our process has to be like what you say, the system has to be in such a way so that the wall is a very good conductor, so so that the transfer of heat energy will be very much will be happening with ease. Okay, so the energy can go and come without being lost. So what is a quasi-static process, that we will see at first. Okay, so quasi-static process means the process is very slow, so that the heat transfer can be happen, because to transfer heat from some material to another material, some amount of time is required. Now if we make the process very fast, so the time to transfer the heat will not be adequate. As a result, the transfer of heat will not be complete, so it will be partial only. So in order to maintain the flow of energy from one system to another system through some, what you say, isothermal uh, separation, the process has to be very very slow. Okay, so what is a nice definition of quasi-static process? The nice definition is that like it is a such slow process in which process the thermodynamic parameters of the system will be in equilibrium in all of the states. That means they all will be balanced in such a way. Okay, the process is so slow that there will be no imbalance between these thermodynamic parameters. Acha. So what to do now? Now see, isothermal processes always follow the gas equation. Now we have seen in our some classes, previous studies, that the gas equation is given by PV equal to RT. Okay, so RT is a constant, so I can say that, yeah, so PV is equal to a constant, right? So what is PV? P is pressure, V is the volume, R is universal gas constant, and T is the temperature. So from Boyle's and Charles formula, we can have the conclusion in such a way. So from this, I can always write P is equal to RT by V. So if I just substitute that thing here, so I know the change in volume will be from V1 to V2. So instead of pressure, I can write here RT will be coming out because it is independent of volume. So this will be V1 to V2, and dV will be dV by V. So if I just do the integration, I will get the work done as RT ln V2 by V1. So this is the work done in our total work done in our isothermal process, where the process will be so slow, so this piston So here the piston will be like in such a way, like it will move or whatever, it will be in such a way so that the, what you say, the process will be very slow. Okay, so that the heat energy will get adequate time to come and go. Okay, so acha, one more thing is there. Uh, we were talking about only heat energy if we provide it, but the processes also can be reversed. Like if I just press the piston, what will happen? The molecules will come close to each other more and more. As a result, the collisions between these molecules will increase slowly, slowly, gradually. So what will happen? The pressure inside the container will increase as well, and the temperature of the molecule will increase because their kinetic energy has been increased such a way, because the collision is happening more and more. So if I just push the piston, the temperature will increase. But if I push the piston slowly, though the temperature will increase, but enough amount of time will be given for this excess heat to come out. Okay, so this kind of process will be isothermal process. Like in this case, the piston was fixed in isochoric process. So, like you cannot give the work. You can just hardly give the energy by giving some extra heat. But here you can do the reverse also. Okay, so the last process which is remained is adiabatic process. So what is our adiabatic process? Let us come into this. This is a little bit different than our isothermal process. You can say the opposite of isothermal process. In this process, what we are going to do? We are going to do the things really fast. So I will, in this, if I has to do this process to our gas system, I has to push the piston really fast in such a like way so that the heat will not get enough time to go out. Sorry. So as a result, what will happen? The temperature inside the gas will increase rapidly. I can give you one example in some survival uh, instinct method. As a method, you see that to like make fire in a wood, what you do, you have a like some sort of bamboo sticks, and then you put one tiny sticks, and you put some sort of cotton or some sort of uh, what you say, like some sort of a ball of a paper here in order to make the like tight. So this will work as piston, and this side will be closed, and here we keep some cotton. Okay, so what they used to do, they used to suddenly with force, they used to just push the piston, this our made piston, in such a way so that the gas inside this chamber will increase in like what you say, the temperature will increase, okay, fast, because the rapid motion of the piston, the gas inside this chamber will be heated up. As a result, this cotton will have some sort of burn, and so with that we can make fire. Okay, so what is happening here, because we are doing this rapidly, the temperature is increasing also rapidly, the heat is not getting enough time to go out. Okay, as a result, the heat inside this chamber is increasing. So this is one kind of adiabatic process, you can say. Now in case of our adiabatic process, we are going to find out the work done. So we know that W is equal to P dV, V1 to V2. If I change the volume in such a way, V1 to V2. But in this case, this condition is followed. So in case of adiabatic process, our that PV by RT, that with that like equation, this equation plays a vital role. So the pressure and volume follows this equation. Now what is this gamma? This gamma is a ratio of Cp by Cv. Now you remember that in the last class we have talked about Cv, specific heat, uh, when we kept volume constant. So this is specific heat. So Cp is the specific heat when we keep pressure constant, and Cv is the specific heat when we keep volume constant. Okay. So gamma is the ratio between them, and PV to the power gamma equal to constant. This is followed in adiabatic process. So this constant is our again RT. So what we can do here, we can again write P is equal to RT by V to the power gamma, and we can put here as well. So RT will come out. This will be dV by V to the power gamma. So if we just do the integration, what we will get? So this is equal to RT has come out, integration dV by V to the power gamma V1 to V2. So if we just do this, RT will be there. Okay. So this V to the power gamma, you can write this. So that will be this, and the limit will be from V1 to V2. If we just put that, we'll get RT by 1 minus gamma, and then this one we will get as V2 1 minus gamma minus V1 1 minus gamma. Okay. So we can even later on we can put, instead of this V2 we can use our temperature as well. Okay, in that equation you can just substitute that value. Okay, so this is the work done in case of adiabatic process. Now in case of adiabatic process, one more thing has to remember, that I told you that when we have a piston and we push the piston rapidly, so that there is no time lag ideally, so the temperature will increase. The opposite is also true. When we just drag the piston out very rapidly, the temperature will fall as well. Okay. So using this we can have some sort of application. Now one experiment you can do in your home, you can take a piece of syringe. You know that there is a piston inside the syringe. You can take some sort of smoke here, and then you can do one more thing. You can just press it harder rapidly while blocking this portion, and you can see what is happening to the smoke. And you can do the opposite also, and you can notice what is happening with the smoke again. So this is one kind of activity given to you. You have to try. You can say this is as a homework. You have to try and you have to write about it. What is your observation, and what do you think why it is happening? Okay, so this is your activity or homework, you can say. Acha. Now we will come to some graph. So we have talked about this processes, isothermal and all those things. Now if we talk about the graphs, how to represent them. Now generally the graph regarding your thermodynamics will be P versus V graphs. These curves are called isotherms. These curves. So if I draw some line like this, so this will be, see, P pressure is constant here, so this will be isobaric process. Okay. If I put a line like this, that will be isocoric process. If I put a line like this, let's say, uh, that will be your adiabatic process. And if I put a line like this, that will be your isothermal process. Now, these two are clear, isocoric and isobaric, why it is so. But this adiabatic and isothermal, how to find out, like how to understand which is which one, because both look same. There is a trick for this. Okay, let me explain you the trick. The trick is that the adiabatic process will have more slope, whereas the isothermal process will have less slope. So let's say this is P versus V graph, and the like gas has been changed its position, like in such a, like its parameter in such a way that the pressure was P2 here, the pressure here is P1, and the volume here is V1, and the volume here is V2. Okay, so these two are the situation. So first, like two separate gases, let's say of the same gases, two separate samples are there, and they are like treated in two ways. One is in adiabatic, one is in isothermal process. Okay, so both are taken in two ways, so they will behave like this. Okay, now why it is so? Because see, the slope here will be dp by dv, right? So we have to find dp by dv in both cases. So we know that in case of isothermal process, our pv equal to rt. So what we can do, we can directly do dp by dv. So what will happen? So this will be dp by dv, and then the outside, like v will be here, then plus we will be having p into dv by dv, which is 1. Okay, so I'm not writing that, and that side will be 0 because this is a constant. So we can see here dp by dv from this equation will come minus p by v. This is the slope. But in case of your adiabatic process, p v to the power gamma is equal to rt. So what will happen if we do differentiation? So it will become v to the power gamma dp by dv plus p. Now gamma will come here, v to the power gamma minus 1, then that will be here, and that side will be 0. So from there we can get that dp by dv is here minus uh, p gamma. Then see, from here we can take out only, so we can take out v to the power gamma. So ultimately this side will be minus v. So this will be divided by v. So you can see, so in case of isothermal this thing is happening, but in case of our adiabatic, what is happening? Let me write here. Minus gamma p by v. So a factor of gamma is coming in case of adiabatic, and that's why the slope is more here, and this is isothermal. So this is the situation. So how to identify which process is adiabatic, which process is isothermal? The more slopier or the more stiffer one, the stiffer one will be adiabatic, and the less stiffer, or you can say like which is having less gradient, that will become your isothermal one. Okay. So these things are there in this like topic, and using, so you can say that this process, where we use this process, these processes are used in our engines, heat engines like car engines, two stroke, four stroke engines, so like our refrigerator. So this kind of procedures are followed. Okay, so this is it. Later on, like we will be talking about more about this chapter and some question numericals also. So bye bye till then.